Welcome to a code report solution video. In this video, we're going to be covering the solution to the problem Chef and Circles from the CodeChef October 2018 long challenge. The problem states there are n circles in a plane. Circle I and circle J form a good pair if it is possible to choose a point P1 on the perimeter of circle I and a point P2 on the perimeter of the circle J, such that the Euclidean distance between P1 and P2 is exactly k. Note that P1 and P2 don't have to have integer coordinates. You should answer Q queries. In each query, you are given the required distance k. Chef is interested in finding the number of good pairs of distinct circles for each query. Please help him. Note that circle I and circle J are distinct when I does not equal J. There may be any number of circles that coincide, i.e. have identical centers and radii. And note that the constraints for this problem are that the number of circles n is going to be between 2 and 10 to the 3, and the number of queries is going to be between 1 and 5 times 10 to the 5th. And those are the two main ones that we need to be concerned with. So let's take a look at the example that CodeChef provided us with. And I just want to comment that props to the person who wrote this problem. I thought it was an awesome problem and a lot of fun to solve. So here's the example that CodeChef provided us with. We're given 2 and 3, and that is n and q, so 2 circles and then 3 queries. So the next 2 lines represent the coordinates of the center of our circle plus the radius of the circle, and then the last 3 lines represent the queries, the length of k that we are trying to look for. And the output for this is going to be 0, 1, and 0. But really, we can't really infer much from this without sort of graphing this out. So let's do that to see what this problem looks like. And we can see here that we have our 2 circles graphed. The first one, the big red one, is our first circle that has coordinates of the center 0, 0 and a radius length of 5. And the second one has center 8, 3 and a radius length of 2. And then we have 3 queries. So it's checking, is it possible to draw a line from any point on the perimeter of the first circle to any point on the perimeter of the second circle that has length 0, length 10, or length 20. For 0, we know it's not possible. This is only ever going to be possible when the circles intersect, which clearly these 2 circles do not. For the k equal to 10, we are going to be able to do this obviously only once because there's only 2 circles, but in an example where we have a lot more than 2 circles, this value is going to be larger. And then for 20, we're not able to do this. So let's take a look at how we can go about trying to find what's the shortest distance that we can draw between 2 perimeters and what's the largest, because that's what's going to motivate our solution. If for every pair of circles, which we know we have the time to calculate because we have only up to 1,000 circles. So by going through every pair of circles, we know that that's quadratic, but because there's only 1,000 of them and we have up to 10 to the 8 operations, this is going to be okay. So for each pair of circles, we're basically going to figure out what's the minimum distance and what's the maximum distance of a line that we can achieve by sort of drawing it between 2 points on the perimeters. And then if we store these in 2 data structures, and then we can use binary searches to figure out how many of the pairs of circles satisfy the given query length k. But before we get to that, let's take a look. How would we find the minimum distance and the maximum distance? So the first thing we need to note is that there's a very important relationship between any 2 circles, and that's the distance between the centers of those circles. And using this distance and comparing it to the radius lengths of our circles, we can figure out basically whether they intersect, whether one is inside the other, or whether it's like this example where they don't overlap at all. And we can see here too that the smallest distance is going to be this little piece here, which is going to be equal to the length of the distance between the 2 centers minus the radius of circle 2 minus the radius of circle 1. And if we look at what the longest distance is going to be possible, we just need to extend this line out to the right and this line out to the left. So it'll look as follows. And hopefully, I don't have the mathematical proof to show you that these are the longest and shortest distances, but hopefully visually just looking at it, you can see that the line that goes through the 2 centers is going to be longer than any other line or shorter than any other line if we shorten it if you can just visualize moving this line down here, it's not going to be as long. So this is the maximum distance that we can achieve. So how can we calculate these two? So the first thing to note is that this is, we've sort of broken this up into three parts: the distance between the two centers, and then the extension on the left and on the right. And in the middle here, we can use the Pythagorean theorem to solve the length. So if you manipulate the Pythagorean theorem, we get the following equation, or you might just know this from high school math if you remember, that the distance between 2 points on a Cartesian plane, the 2 points being x1, y1, and x2, y2, is just the following. So you take the difference and square them, which will get rid of any negatives if you end up having them, and then just square root the sum of those two squares, and that'll give you the distance between each of the 2 points here. So if we plug our values in for this example, we end up with the following, and that is that the pink line here has a length of 8.544. So in order to get the length of this little piece here, which is the distance, the minimum distance between the two circles, hopefully it's clear that all we need to do is subtract the radius of both circles. So here that radius is 2, here that radius is 5. So if we subtract from 8.5447, we get the minimum, which is right here, 1.544. And then to get the maximum, we take our same value d, but instead of subtracting the 2 radii, we add the 2 radii. So we take this pink line and we just add the blue and the red line, which are equal to the radii of each of these circles. So we end up with 8.544 plus 5 plus 2, which is 15.544. So this now represents the range of all possible values that will give us a successful line for a given value k. So we can see here that that's why we end up with 0, 1, 0. 0 doesn't fall into this range, 20 doesn't fall into this range, but 10 does fall into this range. So that's sort of the nice thing about this problem, is that we don't actually need to find what are the coordinates. We don't need to, sort of go around, discretely at some, very small finite amount that, and then find, 2 points on each perimeter that end up equaling k. We can just find the maximum and the minimum and then check, does this fall into this range? If so, we are going to do a +1 for that. So this only covers one case, however. So this is the case where we have the circles not overlapping at all. And we need to cover the other two cases because we can't just use the formula that we used for this case. So there's going to be 3 sets of formulas for the 3 cases. Case 1 is where they don't overlap. Case 2 is going to be where they intersect, their perimeters intersect. And case 3 is going to be where they completely overlap and their perimeters don't intersect. So these 2 examples demonstrate the second and third case that I talked about. So intersections here, and here is the complete overlapping with no perimeter intersection. So once again, this line that connects the 2 centers is going to be important, and it's going to be how basically we determine whether or not 2 circles intersect, overlap, or don't meet either of those 2 criteria. So you can see basically here that to tell that the 2 circles don't overlap or intersect, we can just check that d is greater than the sum of the 2 radii. So you can see here this is the radii of circle 2 and circle 1, and so if d is greater than the sum of those 2, we know that they don't intersect. And similarly, if we have a distance d that is less than the difference of the 2 radii, we know that they're completely overlapping. So that one's a little bit harder to see, but hopefully we can see it by animating this a little bit. So I just reduced the size of this circle so that we have all 3 sort of secondary circles the same size, so it's easy to reason about. And let's move this formula that we're going to need up to the top here, and then here are case 1, 2, and 3. So we've already solved case 1, where we take d and we just subtract the 2 radii and then add the 2 radii to get our minimum and our maximum. And now we are trying to motivate case 2 here, why we can take, or why we can look that d is less than the difference between our 2 radii. So if we slide this yellow circle down so that it's sort of inscribed, and then we extend our length d down here, we can see that, imagine that this is just inside the circle, so that d now is basically equal to the difference between the two radii. So the radii lengths are now 5 and 1, and so that makes the difference between them, the absolute difference, equal to 4. And so as soon as we start to slide the yellow circle up a little bit, d is going to decrease, and it's going to be less than the difference 4. So hopefully by looking at this diagram, you can see the motivation for this formula here, that whenever d is less than the absolute difference between the two radii, we have a circle that is completely, one of the circles is completely overlapped by the other without their perimeters intersecting. So that motivates the second case, and then the third case is just everything else. So if d is greater than the sum of them, then we use this formula. If d is less than the absolute difference, we're going to use this formula that we're going to figure out here in a sec. And for all other cases, that means that the circle, the two circles' perimeters intersect. And for this case, we know that the minimum will be 0 because we just choose the point where, one of the 2 points where the perimeter intersects, and then your length of your distance k is definitely going to be 0. So we only need to figure out what the upper bound for this case 3 is. So let's move our yellow circle back and let's focus on case 3 first. So this section, because we already have half of this. So what is the other half? So in order to motivate this, once again, we're going to slide our green circle out and then extend our distance d to the center. And you can see at this point that the distance of d is equal to the sum of the two radii. So that's going to sort of be our starting point, is that the maximum distance is just going to be this value here, d, which currently is equal to r1 plus r2 plus r1 and r2 again, because once again, we're going to draw this line that moves all the way from end to end. So at this point in time, we basically have the following formula: 2 times r1 plus 2 times r2 plus d minus r1 minus r2. And this works out at the current point in time to be 0. And so what's going to happen here is that when you start to move your green circle in, as it was before, your length d is going to no longer be equal to r1 plus r2. And so this sort of term here is going to start to generate a negative value, and it's going to decrease the upper bound, which makes sense because this total distance from this point here to this point here is going to slowly start to shrink. So this is the formula really that we want, but this can be simplified by canceling out some of the r1s and r2s, and then we end up with r1 plus r2 plus d. But I showed this intermediary step because it's not entirely clear just from looking at r1 plus r2 plus d that that is the upper bound for our case 3. So now that we've done that, we have the upper bound for case 3, and we can reset our green circle. So the only other thing to do is figure out the bounds for case 2, which is when we have one circle inside of the other. So the first thing to note is that it does matter what is the bigger circle and what is the smaller circle that is sort of inside the other circle. So for this problem, we're going to assume that R1, or we're not going to assume, it is the fact that R1 is greater than R2, but note that this could be different depending on your pair. And so what's going to happen here is we can just sort of look at what's the minimum difference here. So that's going to be that amount right here. So if we take a look at this amount, how do we calculate this? It's going to be the radius of the larger circle, which is R1, minus this distance here, which we know is d, minus the radius of the smaller circle, which in this case is R2. And that's exactly what we have here, R1 minus D minus R2. So that's pretty straightforward. It's literally just looking at this graph. We have D, we have the radius of each of our circles, so just putting them together to sort of work out what this piece is. And then for the maximum, it's going to be this amount. So starting from this point, going straight through to the top. And this is simply just going to be the diameter of our larger circle, which is equal to 2 times the radius, obviously. So 2 times the radius minus the value that we just calculated. So here I'm calling this min, but basically this is just the value that we just calculated. And that's easy to see because it's just the diameter minus this value because they complement each other to get the full diameter. So that's the motivation for each of our sets of formulas. I know that took a little bit of time to get through, but really it's actually not that difficult. If you understand the Pythagorean theorem and you're able to draw this out, you can sort of work your way through to getting each of these. I think this is the easiest case. This is the second easiest case, and this one I guess would probably tie for case 2 and case 3. So once we have this, for every single pair of circles, we can generate the minimum and the maximum distance for our value k. And from there, all we need to do is generate these for each pair, and then store them into 2 data structures. We'll call one begin and one end, which is basically the beginning of our range and the end of our range. And then for each query k, we can just use binary searches to figure out how many ranges start before our value k, and then how many of them ended before our value k, which basically getting that difference will tell us how many ranges have started but haven't closed, which means include this value k. So the 2 binary searches that we're going to use in C++ is going to be upper bound and lower bound, and those will match to our beginning end data structures. So that's it for the visualization of this problem. Hopefully this all made sense, and if not, hopefully maybe looking at the code will clarify things a little bit. So let's take a look at our code solution. So here's our code solution. At the top here, we just have some macros and some type aliases to make the code a little bit more readable. And we have 2 functions here, the main function, and then this is going to make a call to our function calculate circle distances, just so that it fits easier onto 2 different slides. So at the top here, we're reading in n and q, our number of circles and our number of queries, and then we're initializing a vector of vectors. The first outer vector is going to be dimensioned by a number of circles, and then our inner vector is going to be dimensioned by 3, which is basically going to store our coordinates of our center of our circle and then the radius. And so then we're just going to read all of these in, and then we're going to initialize 2 data structures, 2 vectors of doubles, begin and end, and then we're using the fill constructor just to initialize this to the number of pairs of circles that we're going to end up having, which is just equal to n times n minus 1 divided by 2. And this is just because of the time complexity. We want this to run as efficiently as possible, and so using the fill constructor is much better than doing pushback, because you have multiple memory allocations then. So then we're going to enter our calculate circle distances function, which will pass the begin and end vector of doubles in by reference. And we'll look at this function in a second, but assume that we have correctly calculated the start and the end of each of our ranges for each pair of circles. Then we have a while loop through the number of queries. We read in our range or distance k, and then as mentioned before, we basically are just figuring out how many ranges have started up until k, and then how many of them have been finished. And so we use that by calculating the distance between the start of our vector and then the iterator that is returned from our binary search function. So upper bound passing in the value k, and then lower bound passing in the value k as well. And note that if you're not familiar with these upper bound and lower bound binary search functions, I've made a video previously that explains the binary search, lower bound, and upper bound functions or algorithms. So take a look at that here, pause the video, go watch that, as I don't want to duplicate the explanation. And then once you have these 2 values, you just output the difference between them, and as mentioned before, this is going to represent how many ranges does k fall in. So taking a look at our calculate circle distances function, we are stepping in here. Note that we have this convenience function dist, which just calculates the distance between 2 points a, b, and c, d, otherwise x1, y1, and x2, y2. This is just the formula plugged in, the square root of a minus c squared and b minus d squared. And then we come in here, so we set our index 0 equal to 0, and then we have a nested for loop, so we're going to get each pair of circles, and then we're just conveniently storing into x1, y1, r1, and x2, y2, r2 our values that we get from our vector of vectors v, and then we quickly calculate our distance d using our dist function, and then we have our 3 cases right here. So if d is greater than r1 plus r2, here's our first set of formulas. If d is less than the absolute value of r1 minus r2, then here are our formulas here. And note that we have 2 different cases. So in the case that r1 is less than r2, we are sort of having R2 and R1 here and then R2 here, but in the other case, we sort of swap the values R2 and R1. So note, we're just plugging in the exact same formulas that we calculated before. And then in our last case, when we have our circles intersecting, we know that the minimum of our range is 0, and that we sort of worked out the formula to be R1 plus R2 plus D. And so at this point, we are at our current index, setting our beginning of our range to our value A that we set up here, and then the end equal to B, and then we post increment our index here. And note that I initially implemented this solution using a multiset, which is equivalent to a vector that ends up getting sorted. But I guess Dennis would be happy to see. Dennis is the C++ code reviewer of the of this channel. He's always advocating for, don't use data structures that don't have good cache coherency, meaning that their elements are stored next to each other in memory. Typically, it doesn't make a difference, but for this problem, it did. When I used a multiset and then, things are automatically sorted for you, it timed out. But switching it to be a vector of doubles and then sorting it at the end and using the fill constructor up front, it did pass the time requirements of this problem. So that's the thing to keep in mind. If you're ever using, non-cache coherent data structures, try switching to a vector and it might solve. So once you've gotten through this nested for loop, you just need to sort these so that you can use your binary search functions on them, and then you're good to go. So I know this was a longer video, but hopefully it was helpful. The last thing to talk about is the time complexity, which for this problem is actually quite complicated. So if we work through sort of the beginning time complexity, we end up with this. So n squared is for this nested loop here, basically calculating the A and B values, begin and end values for each pair of circles. Then we have at the end a sort, which takes place on our number of pairs of circles. So the number of pairs of circles is n squared, so we plug that into our n log n formula, which is the time complexity of sort, and we get n squared log n squared. And outside of this, in the main function, when we were doing the binary search queries on our data structures, we have k queries, and we're doing that on a vector of length n squared. So this is the total time complexity, but when we reduce this, we're going to end up dropping the n squared and then dropping the exponents that are inside the log, because those would just come out in front as a constant. And so the final time complexity is actually going to be n squared log n plus q log n. As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.